academic affairs. So we're going to go through with the rest of the quarter to online means. No? And as part of that, no, decided to do video lectures instead of the usual uh, online means, no, like BB Collab or anything real time, because uh, I want I want to make something that uh, is flexible, no? So video lectures uh, is much more flexible in nature kasi nga uh, you can view it anytime and anywhere. Pwedeng balikan pag may nakalimutan, no? So uh, I came up with that idea, no? So despite na making videos take a lot of work, no? Especially on my part na I have other things to do, no? I will deliver uh, I will deliver uh, the topics, no? That you need to learn uh, online, no? With the best of my ability, no? So for the first part, no, I'm going to discuss the soil bearing capacity for shallow foundations, no. Although I already discussed it during our last classroom lecture, no. Kasi in uh, order to order to really emphasize it, no. So let's begin. There are two things that we need to consider for shallow foundations during design, no? So the first thing is the settlement of the soil that is caused by the foundation. So as you can see, no, the structure transfers the load on their foundation, in which the foundation shall transfer the load on the soil, no. So of course that load from the foundation, no, causes increase in stress in soil. So of course it will also cause the soil to settle at a certain height. And when designing foundations, no, it should be considered that the settlement must be at the minimum level, no? It should be something that cannot be seen by the naked eye, no. So dapat hindi siya nakikita ng rather hindi siya nasusukat ng ruler, no. So pero kung ang settlement niya, no, is something that is drastic, no. So up to a certain point, no, it will lead to what we call the shear failure, no. So shear failure had three types of occurrences, no. Pero we're going to emphasize only the two of them, no. So the first one is the general shear failure, no, and then the second one is what we call the local shear failure, no. So assuming that this is your foundation, no, and then this is your soil, no, the foundation is subjected to the load Q, no, distributed throughout the area, no. uh, it will it pushes uh, the soil downward, no. And let me emphasize to you the two types of failure, no. So the first thing is the general shear failure, no. So this occurs commonly on dense soils, no. So ang nangyayari, no, kapag in-apply natin yung load, no, whenever we apply the load due to the foundation on the soil, no, it causes some parts of the soil to rapidly go upward, no. So if you can see, the failure is divided into three regions, no. So 1, 2, and 3, no. So yung 1, no, the one directly below the foundation, no, and 2, no, is the region 2, and then region 3, no, is the one going upward, no. So sa general shear failure, no, so kapag tinulak ng foundation yung lupa, no, yung ibang parte ng lupa, no, goes upward rapidly, no. Pero sa local shear failure naman, no, usually mas loose ang soil, mas nangyayari ito sa mga soil na mas loose, no, looser than what happens in general shear failure, no. So ang pinagkaiba ni local shear failure and the general shear failure is that mas mabagal ang pag angat ng mga soil dun sa around the foundation, no. So and as observed, no, there are only two failure regions on local shear failure, no. So okay, no. So to compute for the bearing capacity, no, Terzaghi, no, the father of soil mechanics, no, derived a formula, no, to approximate it, no. But of course he considered the following assumptions, no. So the depth of foundation is less than or equal to its width, no. So let me write it down, no. So the d sub f, no, is less than or equal to the width of the foundation, no. So d f is less than or equal to b, no. And next, the weight of soil above the footing may be replaced by a uniform surcharge, no. So we assume that the soil above the footing is the surcharge, no? Okay, no? So other assumptions, no, no sliding occurs between the foundation and the soil, no. And soil beneath foundation is homogeneous semi-infinite mass, no. Number 3, we consider the Moore column failure criterion. And number 4, the general shear failure is the governing mode, but it's not the only mode, no. So we saw a while ago that No? We saw a while ago that the ultimate bearing capacity for local shear failure is much smaller compared to the general shear failure. No? So let's go back here. No? So foundation is very rigid relative to the soil. Soil above the bottom of foundation has no shear strength, only shear charge load against the overturning load. No? So part of the assumption is that uh, this part, no, let me write it down again, no, we assume that this part of the foundation had no overburden pressure, no? So this one, okay, no, so let's go back again. Yeah. The applied load is compressive, no, because soil uh, is mostly a compressive material and applied vertically to the centroid of the foundation, and then no applied moments present, no. So how did Terzaghi derive the formula, no? We should refer to this triangle, no, so no, Terzaghi use uh, the summation of forces, no, uh, in order to derive no, the ultimate bearing capacity, no. So as you can see, no, this QU is the ultimate bearing capacity, no. Let me emphasize to you that uh, this is assumed to be a strip footing, no. So what do we mean by strip footing? It's like this one, no. So it's a long wall. Going back here, no. So this is the ultimate bearing capacity, no, and then this is the weight of the soil, and then the weight of the soil pushes the soil downward, but is resisted by the cohesive force, no, or the cohesion, no. So it will deriving it will belong. So let me just give to you the derived formula for the general shear failure, no. So these are Terzaghi's bearing capacity formula for general shear failure. The first formula are for strip footings, no. So strip footings, these are how it look like, no. So it's a long wall footing subjected to a distributed load, no? So okay, so the Q ult for strip footings is CNC plus QNQ plus 0.5 gamma B and gamma, no. For square footings, no, Q ult is equal to 1.3 CNC plus QNQ plus 0.4 gamma B and gamma. For circular footings, it's equal to 1.3 CNC plus QNQ plus 0.3 gamma B and gamma. So these are all derived formula, depending on the shape of the footing. So the C is the cohesion, Q is the overburden pressure, no? So if you're familiar with uh, if you're familiar with stresses in soil, no? So Q is equal to, let's say, you have a unit weight of soil, no? So Q is equal to gamma dF. Then gamma is, of course, the unit weight of soil, and B is the dimension, the width of your footing. NC, NQ, and N gamma are NC, NQ, and N gamma are uh, bearing capacity factors. No? Uh, This can be found uh, in some textbooks, no, in a form of a table uh, depending on your phi, or known as the angle of friction, no. So most of the time you will be given an angle of friction, and then you will be able to determine the values of NC, NQ, and N gamma, no. O nga pala, no, let me tell you, no, this is a generalized equation, no, assuming that the shape of your footing is rectangular, no. So Q alt is equal to 1 plus 0.3, no, multiplied by B over L, no, the CNC plus QNQ plus 0.5 multiplied by 1 minus 0.2 B over L quantity, no, gamma B and gamma, no. B is less than or equal to L, no. For local shear failure, no, it is just the same as the general shear failure, but we can just use the following formula. So C bar is equal to the 2/3 of C, and then tan phi bar is equal to 2/3 of tan phi, no. So your C and your phi here are your shear strength parameters, no, considering the general shear failure. C bar and phi bar are your shear strength parameters, no, considering the local shear failure, no. And then your N prime C, N prime Q, and N prime gamma are the ones to be used, no, instead of the usual NC, NQ, and N gamma for general shear failure, no. So here is a table representing the Terzaghi's bearing capacity factors for general shear failure, no. And this is how the graph looks like, no. So this is I already gave you a handout containing the tables and the graphs for the values of NC, NQ, and N gamma. So you may just refer to that, no, when solving different problems, no. For phi is equal to 0 degrees, no, NC is equal to 5.7, NQ is equal to 1, and N gamma is equal to 0. These are the values for bearing capacity factors for local shear failure. This is N prime C, N prime Q, and N prime gamma. N prime C, N prime Q, and N prime gamma. And this is the graph. So we're going to solve sa an example to for this topic. So we're going to solve a sample problem, no, for this one, no. So from your notes, no, I decided to separate the part that tackles only the one that we've discussed in this video, no. So a square footing that is 1.5 meter by 1.5 meter in plan, no, the soil supporting the foundation has a friction angle of V is equal to 20 degrees and a cohesion of C is equal to 15 kilopascal. The unit weight of soil gamma is 17.8 kilonewton per meter cube. So you are to determine sa your Q old, no, for letter A, general shear failure, letter B for local shear failure. Then assume that the depth of your footing is 1.00 meters from the top of the soil. And when we say depth of the footing, no, this means the bottom of the footing, no. So your depth is measured from the natural grade line, no. So this is your natural grade line up to the bottom of your footing. This is your DF. Okay, no. So you have your C, you have your Q. You can be able to solve for Q, and then you have your gamma, you have your B, no. So we only need the Terzaghi's bearing capacity factors, no. So we either look at the table, no. You're given a angle of friction of 20 degrees, no. So if your angle of friction is 20 degrees, so therefore the values for NC, NQ, and N gamma will be this one, no. NC is equal to 17.69, NQ is equal to 7.44, and gamma is equal to 3.64, no. So let's try looking at the graph, no. Okay, this is your angle of friction 20, no. So NC is equal to this one, so it is approximately equal to 17.69, no. So this is 20, no. Yeah, that is your NC. NQ is this one, NQ is approximately 7.44, so somewhat in between 7 to 8, and then your N gamma is 3.64, no. So somewhat it's near to 4, no? So we can be able to compute for Q alt, no. Q alt, no, Q O oh, Q alt is equal to, no? So the formula for square footing is 1.3 CNC plus Q NQ plus 0.4 gamma B and gamma. Okay, so 1.3, no? 1.3, the value of C is equal to 15 kilopascal. 1.3 times 15 times 17.69 plus Q. Your Q is equal to your gamma DF. So Q gamma, your gamma is equal to 17.8 multiplied by 1 multiplied by 7.44 plus 0.4 17.8 1.5 gamma B gamma B N gamma. Your N gamma here is equal to 3.64. So you have to make sure that you calculate it correctly. So I'm going to calculate it. 1.3 15 7.69 plus 17.8 times 1 times 7.44 plus 0.4.8 times 1.5 times 3.64. Your Q alt, no, is computed as 361.26 kilopascal. Okay, this is for general shear failure. Okay, next we're considering now your local shear failure. For local shear failure, that's right. Local shear failure. No? So your C is equal to 2/3 of your C. No? 2/3 of 15. No? Therefore, that is equal to 2/3 of 15 is equal to 10 kilopascal. Next, your tan phi. Tan phi bar is equal to 2/3 tan phi. And then your phi bar is equal to, no? So inverse tangent of 2/3 tangent of 20. No? So that is approximately equal to 13.63 degrees. No? 13.64. 13.64 degrees. Okay? No? So from the tables or the graph, no, since we don't have the corresponding values for approximately 13.64, no, we can either interpolate this one. We can either use linear interpolation or just use 14 degrees, no. So you may try interpolating, no, or you may we may also use the next value, which is 14, no. I will let you try interpolating this one, no, but I will assume, no, I will try to use 14, no. So I use phi is equal to 14 degrees, okay, no, but this may give a huge discrepancy from the actual value of phi. Okay, so for q alt is equal to 1.3 c n prime c plus q n prime q plus 0.4 gamma p n prime gamma. Okay, so your q alt is equal to 1.3, then multiplied by 9.31, no, plus 17.8 multiplied by 2.55 plus 0.4 17.8 times 1.5 times n gamma 0.48. So let's try to compute it using the calculator. 1.3 times 10 times 9.31 plus 17.8 times 2.55 plus 0.4 times 17.8 times 1.5 times 0.48. This is equal to 171.55 approximately kilopascal. So this is for local failure. So on the next video, we're going to try considering, the effect of the water table, no, on the bearing capacity of soil. No? So stay tuned.